Hello everyone, my name is Yu-Chuan Liang. Today I would like to present icLibFuzzer, an isolated context libFuzzer for improving fuzzer comparability. libFuzzer is a strong fuzzer that has helped find thousands of bugs in real-world programs. However, fuzzers that seek to compare with libFuzzer face some issues, which limit them to compare with libFuzzer over certain metrics and datasets. Or even worse, libFuzzer may produce wrong results if they try to run on arbitrary programs. This will present icLibFuzzer, which solves these comparability issues, and our preliminary evaluation shows that icLibFuzzer may serve as another competitive evaluation baseline for fuzzing research. Here is our outline. We will first give some introduction and background on fuzzing and libFuzzer. Then we will mention some comparability issues of libFuzzer when comparing it with other fuzzers such as FL. After that, we will present our solution, icLibFuzzer, with its implementation details and preliminary evaluation results. At the end, we will give our conclusion and future work. First, let's give some introduction on fuzzing. Fuzzing is a technique that tries to automatically find an input which can trigger abnormal behavior of a target program, for example, crashes or hangs. The fuzzer, namely the fuzzing engine, first generates an input and feeds it into the fuzzing target. After the fuzzing target exits, the fuzzer will collect information and generates next input based on previous input and collected information. libFuzzer is one implementation of fuzzer. It is a coverage-guided fuzzer, which means that if an input can trigger new code coverage, it will be saved to generate preceding inputs. As its name shows, the fuzzer targets to fuzz library functions. However, due to some issues we will discuss later, the fuzzer is seldom being compared with other fuzzers. Therefore, some advanced techniques in libFuzzer seem to be left unnoticed in state-of-the-art academic papers. To show the strength of libFuzzer, we choose to explain some of its advanced features that are not yet being fully adopted by other fuzzers. The first one is CMP tracing. Take the code snippet as an example. In line 2, this program will read in a short int into the variable magic. Then in line 3, it will compare it with the magic number. If they are equal, then the bug will be triggered at line 4. So how CMP tracing works here is libFuzzer will insert a function call at line 3 while compiling this program, which will store the compared arguments, namely magic and hex 1234, into a bitmap. The bitmap will then be analyzed when generating next input. For example, if our first input is hex ABCDFF, then at line 3, the function will store a pair of hex ABCD and hex 1234. When generating next input, libFuzzer may analyze the stored information and tries to replace 2 bytes in the input with hex 1234. Now let's take a look at another advanced technique, value profiling. It is the same code snippet except that libFuzzer inserts another function call at line 3. This function will store the distance between compared arguments, for example, the Hamming distance of binary forms, into a bitmap. The bitmap will be analyzed to decide whether this input makes any progress on passing the branch condition. For example, if we input hex 1245, then at line 3, it will record the Hamming distance between hex 1245 and hex 1234. After the fuzzing target exits, the fuzzer will check if the Hamming distance becomes closer compared with previous input. If it does not become closer, then the input is discarded. If it does become closer, then this input may be used to generate next input. With value profiling, the fuzzer can try to pass a hard branch condition progressively. Even though libFuzzer employs some advanced features and performs well on finding bugs in real-world programs, it is seldom being compared with other fuzzers due to some comparability issues. One of the main reasons causing these issues is the infrastructure design of libFuzzer. libFuzzer adopts an in-process design for achieving high execution speed. The workflow on the right side is a fuzzing procedure. In the second step, marked by the red box, libFuzzer treats the fuzzing target as a callback function, which in turn forces the fuzzer instance and fuzzing target to share the same context. For example, virtual memory space. In fact, sharing the context is the main reason causing the comparability issues. Now let's see what exactly are the comparability issues. First issue is that libFuzzer lacks support of common evaluation metrics of fuzzers. As fuzzer instance and fuzzing target share the same context, when fuzzing target crashes, libFuzzer will crash immediately since it may not be able to recover from the broken context easily. Also, it expects the user to fix the bug before keep going on fuzzing. This makes libFuzzer hard to compare with other fuzzers over the same metrics. Here are some common metrics we have seen in fuzzing papers: code coverage, number of bugs found in the fix time, and time to find all intended bugs. Obviously, it is hard to measure libFuzzer's progress using these metrics, since libFuzzer will terminate immediately whenever the fuzzing target crashes. Moreover, the crash may be triggered by a polluted global context rather than the program's bug. Therefore, previous work can only compare with libFuzzer over the time to first crash metric, compared on fine-tuned datasets, or enable the ignore crash mode. The first two options limit the comparison scope, while the third option, ignore crash mode, can only solve the problem partially, as it simply restarts the fuzzer instance whenever a crash occurs. This cannot avoid broken context caused by non-crash bugs, which we will discuss later. Even though ignore crash mode can continue after finding the crash input to the fuzzing target, it may produce wrong results for programs expecting a clean global context. We identified two cases that ignore crash mode cannot handle or may behave wrongly due to context pollution. Now let's go through each of them. The first case is when fuzzing target depends on global variables. In C programs, we may assume that global variables will be initialized before main function start. However, since libFuzzer treats the fuzzing target as a callback function, some initialization will not happen again when you run the fuzzing target again. Take the code snippet below for an example. The function getOpt is widely used in many open source projects, which will parse the command line arguments. This function depends on a global variable called opt_nd, which indicates the next element's index of the command line arguments. Now assume that the fuzzing target uses getOpt to parse the command line arguments, and libFuzzer feed the arguments in the red box below to the fuzzing target. Before the first round of fuzzing target, the global variable opt_nd will be initialized as 1 at the startup time correctly. However, after the first round of fuzzing target exits, opt_nd may become 3, which indicates that the next index of element to be parsed in the command line is 3. This will cause the second round of fuzzing target to behave incorrectly. Secondly, when memory leak exists in fuzzing target, the memory leak will persist and keep consuming the memory until libFuzzer crashes and restarts. As the picture shows, memory usage will keep growing if memory leak persists. Here we present icLibFuzzer, our solution to these comparability issues. Inspired by AFL, we separate the fuzzer instance into two components, main controller and ForkServer. Each of them is a standalone process. The main controller runs almost the same as the fuzzing procedure we mentioned before. However, in the second step, marked by the red box, instead of running the fuzzing target itself, main controller informs ForkServer and leaves the job of running the fuzzing target to ForkServer. Now on the ForkServer side, it treats the fuzzing target as a function, as InProcess design does. However, instead of calling the function directly, ForkServer will fork a child process and run the fuzzing target in the child process. So when ForkServer gets a notification and an input from the main controller, it will fork and run the fuzzing target. After the fuzzing target exits, the ForkServer will inform the main controller and wait for the next input. Here we want to emphasize that since main controller and ForkServer are different processes, the information collected in ForkServer, for example through CMP tracing or value profiling, need to be somehow transferred to main controller. We choose shared memory here as a fast inter-process communication method. That is, we map every data structures stored in the collected information onto shared memory. While implementing the ForkServer design, we observe that the primary factor affecting the forking speed is the writable memory size of the ForkServer. Remember that we will map every data structure that stores information collected from fuzzing target onto the shared memory. The idea of structure packing is, instead of mapping the data structure one by one onto the shared memory, we map them all in one onto a contiguous shared memory space in order to avoid fragmentation and minimize the memory usage. This technique helps us approximately double the execution speed on several real-world programs, as we will show in the results later. Now let's compare InProcess with ForkServer infrastructure. For the InProcess design, fuzzing target is a callback function of fuzzer instance. Therefore, both of them share the same context. As the animation shows, if the fuzzing target pollutes the context, for example modify the global variables, then the pollution will persist in the context after the fuzzing target exits, influencing the preceding runs of fuzzing target and fuzzer instance. In contrast, for the ForkServer design, the fuzzer instance consists of a main controller and a ForkServer, fork the fuzzing target from ForkServer. Thus, the contexts are isolated between fuzzing target and fuzzer instance. So as the animation shows, even if the fuzzing target pollutes the context, when the fuzzing target exits, the pollution will be eliminated and will not influence the preceding runs of fuzzing target. However, the ForkServer will have to call the function fork in every execution of the fuzzing target. It will introduce extra overhead compared with InProcess design. We will show the execution speed difference in the preliminary evaluation results later. In short, InProcess design is more fragile to context pollution compared with ForkServer. However, InProcess is much faster than ForkServer design. Finally, let's see our preliminary evaluation results. Here is our experiment settings. We run our experiments on a 32-core AMD processor with 64 GB memory, using Ubuntu 18 as the operating system. We choose 4 other fuzzers to compare with icLibFuzzer. AFL and HomeFuzz, same as libFuzzer, are adopted by OS's Fuzz project. QSIM and Angora are 2 state-of-the-art fuzzers in 2019. All of the fuzzers we list here, including our icLibFuzzer, use the 2019 version. We run each binary 8 times without initial seed, which means that fuzzers start fuzzing from an empty input. As suggested by one of the previous works, fuzzing without initial seed may be a fair method to compare different fuzzers. We run each binary for 72 hours for rather stable results, different from before as most previous work fuzzed for less than 24 hours. For the code coverage, we use LLVM-conf to calculate the code coverage information for every fuzzer. First, let's take a look at the code coverage results. The y-axis represents code coverage, and the x-axis represents how long the fuzzers run. There are three phenomena we want to point out in our preliminary evaluation. First, icLibFuzzer, represented by the red line, outperforms other fuzzers on most of the binary we test. This may imply that icLibFuzzer can become a competitive baseline for fuzzing research. Secondly, we can see that icLibFuzzer can still find new code coverage steadily after 24 hours, indicating that fuzzing results within 24 hours may be insufficient to represent the fuzzer's capability to find new bugs or cover additional code. Thirdly, even though Angora shows better performance than AFL in its original paper, we can see that Angora, represented by green line here, does not perform well in our experiments. One plausible reason may be that Angora highly relies on initial seeds, at least for these 6 programs we tested. It needs further investigation on how to select initial seeds for Angora wisely. Besides code coverage, we also compare the speed difference between original libFuzzer and icLibFuzzer. Due to the comparability issue we mentioned before, we can only run libFuzzer on Fuzzer Test Suite, a fine-tuned dataset dedicated for libFuzzer. As shown in the table, icLibFuzzer is 4 to 50 times slower than original libFuzzer. This is mainly caused by the overhead of fork system call. However, its execution speed is almost the same compared with AFL. We also record the execution speed of all the fuzzers we test. The results show that icLibFuzzer have competitive execution speed comparing with other fuzzers. Finally, we evaluate structure packing on several real-world programs. In the table, the exec/s represents the execution speed, and the RSS represents the memory size. On average, structure packing halves the memory of ForkServer and double the execution speed, compared with naive implementation of ForkServer. We observed an interesting phenomenon while doing our experiment. The y-axis in the picture represents the execution speed in average, and the x-axis represents the number of simultaneously running fuzzing threads. As the picture shows, the execution speed drops rapidly while the number of simultaneously running threads increase. This is actually investigated by previous work, and the reason is that some resources in Linux kernel cannot be shared by multiple processes at the same time. This should aware us that when we try to run experiment in parallel, we should keep an eye on the number of fuzzing threads. For example, if we want to run icLibFuzzer on objdump for 30 times, we cannot split the experiment into 10 plus 20, as the speed will differ significantly, making the result meaningless. Now here is our conclusion and future works. Since libFuzzer lacks support of common evaluation metrics and suffer from context pollution problem, the advanced features in libFuzzer seem to be left unnoticed by most state-of-the-art academic papers. Thus, we propose icLibFuzzer, which improves the libFuzzer's comparability with other fuzzers, and the preliminary evaluation results show that icLibFuzzer may become a competitive baseline in fuzzing research. There are several possible future works. First, we want to investigate more on the impact of initial seeds and how to choose them wisely. As we mentioned before, Angora does not perform well in our experiment, probably due to the lack of initial seeds. Secondly, there might be ways to further improve the fuzzing speed of icLibFuzzer, for example, through implementational optimization. Since the fuzzing speed is highly related to the code coverage in a fixed time. Thirdly, a cache-aware structure packing may be needed, as a misalignment of data structure may be a potential side effect of structure packing. Thank you for listening.